Have you ever observed what happens to the strings of a guitar when they are strummed? Not only do these strings vibrate when you strum each of them, you'll see that they take certain shapes while vibrating. Why do these strings take these shapes? And what is this kind of motion that causes vibration? In simple words, you'll see that they are performing repetitive motion. They're doing the same thing again and again, possibly going up and down in various shapes. The strings of a guitar are an example of the shape strings take when fixed between two ends. And this is an example of a type of oscillation or a repetitive motion. In everyday life, there are a large number of repetitive motion examples. And just like the strings of the guitar, they are all known as periodic motion because they take place again and again after a fixed interval of time. So basically, every time a motion repeats itself after a certain interval of time, it is known as periodic motion. Now, we have seen an example of periodic motion in a chapter, that is rotation. Rotation was also periodic motion because the motion repeated itself after a certain interval of time. But today, of course, we are going to focus on oscillation or oscillatory motion, which is also a type of periodic motion. And therefore we say that what exactly is oscillation? Oscillation is nothing but the movement of an object between two fixed points, or we can say it is to and fro motion. And that's why we can also understand that all oscillatory motion is periodic, because oscillation is a type of periodic motion. But the reverse is not true. That means that every time you see periodic motion, it's not necessary that it is oscillation. For example, the rotation or revolution of the earth is periodic motion, but it's not oscillation. That's rotation in that case. However, I can also have a combination of these motions which can still be periodic. So every time you see something periodic, it's not necessary that it's oscillation, but every time you see oscillation, it's definitely periodic motion. I also want to take this time to point out right off the bat what is the definition of oscillation. By definition, oscillation is that motion in which the restoring force exists. Restoring force is the force which directs the object always back to the mean position, that is the starting position or the position of zero displacement. And this is what we actually define oscillation by when we talk about it, and it's important to remember that oscillation requires a restoring force, and it requires such a restoring force that it should always pull the body back to its starting or the mean position. So now that we have understood very basically what oscillation is, let's now start understanding the concepts related to oscillation. The most famous example of oscillation is the grandfather's clock or the pendulum clock. We've seen this pendulum swing many times, and this is an example of periodic and oscillatory motion. But these concepts of oscillatory motion and periodic motion, in particular, they require some knowledge of fundamental concepts like period, frequency, displacement, amplitude, phase, etc. So let's see what these concepts mean. I want to start by understanding what exactly is the time period. By definition, it is the smallest interval of time after which the motion is repeated. Now, before I write down the formula for time period, I want to ask the question, what exactly do I mean by one oscillation? I'm saying that time period is the time after which the motion repeats itself, which means it's the time taken for one oscillation. But what exactly is one oscillation? If I take a look at this example where I have a pendulum, then this pendulum initially is at rest at the line A. And when this pendulum starts to swing, it will go from A, first it will move to B, and then from B it will come back to A, and from A it will then swing towards C, that is the other side, and now it's going to come back to its initial rest position, that is A. So you see this motion where the pendulum goes from A to B to A to C and back to A, this entire motion together is known as one oscillation, and the time taken to complete this entire motion is the time period. And therefore we say that this is nothing but the time taken to complete one oscillation or the time after which the motion repeats itself. But actually, in general, what happens is that the oscillation happens so fast that you can't measure the time for one oscillation, and therefore, practically speaking, usually when we measure the time period, we measure the time taken for a large number of observations. For example, we might record the time taken for 5 oscillations, and once we have the time taken for 5 oscillations, then I get the time for one oscillation simply by dividing that by 5. So in general, the time for one oscillation will be given by the total time for n oscillations divided by n, where n is the number of oscillations whose time you measured. So this is how in general, in practically, you will find the time period. Now from the time period we can move on to the frequency, which is nothing but the reciprocal of the time period, and it gives the number of repetitions that occur per unit time. That is how many times, for example, this pendulum is swinging in a second or in a minute. That's the meaning of frequency. And this quantity is called the frequency of the periodic motion, and by definition then it will just be the reverse of time period, that is the reciprocal of time period, that is n is equal to 1 by t. So we learned time period and frequency. Let's now understand displacement. Now actually, you have heard this word displacement before in motion in one dimension, in motion in two dimension, even in scalars and vectors. And you must be thinking that displacement is nothing but the line joining the final point to the initial point. But actually, that is only one type of displacement. Displacement in general means any physical property that is changing with time. And in case of a pendulum, it may be something different. Now first off, let me tell you that it is convenient to measure the displacement of the body from its equilibrium or the rest position. In terms of the simple pendulum, the angle that it makes from the vertical is what we call as the displacement. So let's see what would be the value of this displacement. Now displacement can be positive or negative. If this pendulum starts to swing in an anti-clockwise direction, as the red shape increases, we say that the displacement is increasing. It's moving in the anti-clockwise direction and hence the displacement is negative, but the displacement is increasing in magnitude. And therefore when it starts coming back to its rest position, we say that the displacement is decreasing because it is now coming back to its original position. On the other hand, if the pendulum is swinging in the clockwise direction, then the displacement is positive and it is increasing, and when it's coming back, the displacement decreases in magnitude, but the displacement is positive as long as it's in the clockwise direction. So displacement, like I said, can be positive or negative. Now in general, displacement can be written as a mathematical function of time, and this is obvious because displacement is changing with time. But in particular, when you are writing down the displacement for periodic motion, then this function itself is periodic in time. So what does this mean? This sounds fancy, but let's think about it. The motion is periodic, which means the motion is repeating. So to describe a repeating motion, I need a function that also repeats. So I'm saying that for periodic motion, you need a periodic function, and one of the most famous periodic functions that we know is the cos function, and therefore we use the cos function to describe displacement, and therefore displacement is given by ft is equal to a cos omega t, where omega is nothing but the angular frequency, and this is equal to 2 pi n, or I can say it is equal to 2 pi by t, as we have already seen before. So omega is the angular frequency, and I can describe displacement using a cos function. But the question is, what exactly defines what is periodicity? We have already said that periodic motion means that after some time the motion will repeat itself. So I can write this down mathematically, and I say that ft is equal to f t plus capital T, where capital T is the time period of the motion. Now this is fancy maths, but what does this exactly mean? It means that if I look at an object and I write down what is its displacement, and then I look at that object again after the time period has passed, then that object will be at that same position. For example, if today I look at the position of the earth, then after 365 days, if I look at it again, then the position will be exactly the same. And why is it exactly the same? Because 365 days have passed. And what is 365 days? It is nothing but the time period of revolution of the earth around the sun. And therefore we are saying that if you look at the motion of the object after a time period, then the position is the same, and this is the condition for periodicity. Now, obviously, I said that to describe a repeating motion, you need a repeating function. But cos function is not the only repeating function we know, and we know another function, that is the sine function. And therefore, we can also use the sine function for oscillation or periodic motion in general. And in fact, you will see that in some books, when you read, they will describe oscillatory or periodic motion using a sine function, and sometimes they'll be using a cos function. Don't get too worried. Overall, they are actually the same function, as we'll see in a bit, but you can use either of them to describe the displacement in periodic motion. But you can also do one other thing. You can use a combination of these two functions and also use that combination to describe periodic motion. So for example, now if I have to write down the linear combination, I will say that the displacement can be described as a sine omega t plus b cos omega t. So I'm using both the functions to describe the displacement. Now, instead of writing it like this, sometimes you'll see that they have not written it in two different terms. So here we have written it as an addition of the two familiar terms. But sometimes they might not write it like this, they'll write it in another way. And how do we write it in another way? You assume that a is r cos phi, where r is some new variable and phi is a new variable again. It's a new angle. Similarly, I will assume that b is equal to the same r but sine phi of that angle. If I do this and I put these values into the equation ft is equal to a sine omega t plus b cos omega t, then after putting it into that equation, and then if I use the identity sine a plus b is equal to sine a cos b plus cos a sine b, then in such a case I will see that I can write down the displacement as r sine omega t plus phi. So I have written down the entire linear combination as one term, r sine omega t plus phi. And what is the relationship between the two new variables, that is r and phi, with the two old a and b? It is given as r is nothing but the square root of a square plus b square, and phi is nothing but tan inverse b by a. So this way we have converted that equation, which was written as the addition of two terms, into one single term, but we have gone from two previous variables, that is a and b, to two new variables r and phi, and therefore both are equivalent. Now, just like oscillatory motion is a type of periodic motion, simple harmonic motion is also a type of periodic motion. Here we have this particle connected to the spring, and if I push the spring and release it, then this particle undergoes oscillations. And it does so between the two fixed limits minus a and plus a. SHM is not just any periodic motion, but it is that periodic motion in which displacement is a sinusoidal function of time. This means that if the graph of displacement versus time is plotted, it will reveal that the values of displacement form a continuous function of time. Let's say that the particle at time t is equal to 0 is at an extreme position, that is, at the maximum extent on one side of the mean position. In such a case, when the particle starts moving and reaches the mean position, 1/4 of the total time it takes to perform an oscillation has passed. And therefore, we plot the point t is equal to capital T by 4 and plot the displacement, that is 0. Similarly, now as time passes, the block moves to the other end. Now half the total time period has passed and its displacement from the mean position is minus a. Then the block moves back to the mean position. Now the time passed is 3t by 4 and its displacement is 0 again. Finally, we can plot the final point in this first oscillation, that is at time t is equal to capital T, the block returns to its original position, that is at plus a. And if you continue to plot the displacement of such a particle with time, you will see that the curve obtained is a sinusoidal wave. And therefore, this oscillation is simple harmonic. The equation of simple harmonic motion is a second-order differential equation in x, where x is the displacement of the particle at any given instant of time. This equation is given by d square x by dt square plus omega square x is equal to 0, where omega is the angular frequency given by the root of k by m and is considered a constant. The solution of this equation is the mathematical function used to describe displacement. The general equation for this displacement x is a cos omega t plus minus phi. Now naturally, the next question is what exactly is this phi? We will see this in just a few minutes. If the particle begins from an extreme position, then this equation will change to x is equal to a cos omega t, which means that phi will have a value of 0. Similarly, if the particle begins from the mean position, then this equation changes to x is equal to a sine omega t, which means that phi must be pi by 2. So you see, the equations B and C are special conditions of the equation in A. Under special conditions, we derive the equations B and C from A. We must also keep in mind what exactly is the amplitude of such a motion. It is nothing but the maximum displacement of the particle from the mean position. This could be on either side of the mean position as shown. Finally, let's also discuss what is known as the phase. If the amplitude of the motion is fixed, then the state of motion is determined by the argument, that is the quantity in the brackets omega t plus phi. This quantity, which depends on time, is known as phase. The value of the phase at t is equal to 0 is phi and is known as the phase constant or the initial phase or simply the epoch. So now we can see how the general equation x is equal to a cos omega t plus phi changes when the particle starts from an extreme position or a mean position. Let's say that the particle is starting from an extreme position. In such a case, at time t is equal to 0, the displacement will be plus a, and this is possible only with the cosine function, and therefore this means that phi must be 0 so that x is equal to a cos omega t, and at t is equal to 0, I get x is equal to a, which I need. Similarly, the particle could also start from the mean position. In such a case, you will see that at t is equal to 0, the displacement should be 0. And therefore, when I plot this displacement with time, I see that for this case, I will need a sine function, and therefore phi must be pi by 2, so that x is equal to a cos omega t plus pi by 2, which gives me a sine omega t, and the condition that at t is equal to 0, x must be 0 is fulfilled. From the figure, we can now see that in case of the two waves, the blue wave and the pink wave, they both have the same amplitude A and the same omega, but differ only in their initial starting points. And thus we say that they differ only by their phase angle phi. Finally, we can also write down the time period of the simple harmonic motion. The formula for t is 2 pi by omega, which is nothing but 2 pi by root k by m, which is 2 pi root m by k, which is also written as 2 pi root x by a, where a is the acceleration and x is the displacement at any given instant of time. From time period, it is very simple to write down the frequency, which is nothing but the reciprocal of time period, and therefore frequency is 1 by t, which is omega by 2 pi, equal to 1 by 2 pi root k by m, equal to 1 by 2 pi root a by x. So these are the different concepts related to simple harmonic motion. A useful way of analyzing simple harmonic motion is by studying its association with uniform circular motion. Simple harmonic motion can be considered to be the projection of uniform circular motion on the diameter of a circle in which the uniform circular motion takes place. To do this, let's study the motion of a particle P, which is known as the reference particle. This particle performs uniform circular motion with some constant angular speed omega. This circle, which helps us study simple harmonic motion, is known as the reference circle. The center of this circle is the point O, and OP dash is then the projection of the point P on the y-axis. A is the radius of the reference circle. Observe closely how the projection OP' moves as P performs uniform circular motion. You will notice that OP' undergoes simple harmonic motion. This is evidenced by the fact that the length of OP', which is nothing but the location of P', is given by y, which is a function of t, is equal to a sine omega t plus phi. And this is nothing but the equation of simple harmonic motion. Thus, the projection of the particle P, which performs uniform circular motion onto the y-axis, gives us simple harmonic motion. The point P' is performing simple harmonic motion. Now, in general, initially at time t is equal to 0, the point P may not always begin from the x-axis, and hence it could have some initial phase phi, that is the angular position at time t is equal to 0 is in general phi and not 0. And then as the particle P moves from t is equal to 0 to some other instant of time t, it moves an angle given by omega t, and hence the new angular position of the particle P at time t, and hence the angular position of the particle P' at time t is omega t plus phi. Similarly, simple harmonic motion can also be considered to be the projection of the point P on the x-axis. In such a case, we say that the projection of the position vector of P on the x-axis gives the location x of P', and hence we can write that x, which is a function of t, is equal to a cos omega t plus phi. In this case, the simple harmonic motion takes place about the x-axis. P' is performing simple harmonic motion. Note that this is a very convenient way of understanding simple harmonic motion with respect to uniform circular motion. However, the forces in each of these motions are wildly different. Uniform circular motion requires a centripetal force, whereas the simple harmonic motion requires the restoring force. The velocity of an object in simple harmonic motion can also be obtained by the method of the reference circle. First, we note that the speed of any particle in uniform circular motion given by v is equal to omega a, where omega is the angular speed and a is the radius. This can be used to find the velocity at any given instant of time for a particle in simple harmonic motion. The direction of velocity at time t is along the tangent to the circle at the point where the particle is located at that instant. If this velocity is resolved along the y and the x-axis, it is clear that the velocity acting along the x-axis is given by minus v sine theta. The negative sign indicates that the velocity points towards the decrease of the magnitude of x. Now, if we ask the question that if a particle is performing simple harmonic motion along the x-axis, then what would be its velocity at any instant? And it will be this v sine theta that we have found. Hence, the velocity of the particle executing SHM along x-axis will be minus v sine theta. But since v is equal to a omega, we get the velocity in SHM is equal to minus a omega sine omega t plus phi. This is equal to minus omega root a square minus x square. Using the method of the reference circle, we can also find the instantaneous acceleration of a particle undergoing SHM. Just like velocity, we will find the acceleration of the particle performing UCM along the x-axis, and that will be the acceleration of the projection along the x-axis, which is the acceleration of the simple harmonic motion. For the particle performing uniform circular motion, the centripetal acceleration points towards the center of the circle. On resolving this acceleration along the x and the y directions, we see that the acceleration of the particle along the x direction is given by minus AC cos omega t plus phi. And from the understanding of uniform circular motion, we know that the centripetal acceleration is nothing but omega square a, and therefore acceleration of particle in SHM will come out to be minus omega square a cos omega t plus phi. This can be written as minus omega squared x of t, because x of t is nothing but a cos omega t plus phi. This gives us another important property of simple harmonic motion. That is, the acceleration of a particle is proportional to its displacement. Now, if for simplicity we consider that phi is 0 and we plot the displacement, velocity and acceleration graphs in simple harmonic motion, we will see that these graphs vary sinusoidally with time. However, their initial starting points are all different, and their maximum and minimum values are also different. And on comparing these three graphs, we see that the phase difference between velocity and displacement comes out to be pi by 2, between velocity and acceleration comes out to be pi by 2 as well, and between displacement and acceleration comes out to be pi. Now we must also remember one other important thing. The graph of velocity and displacement will come out to be an ellipse, whereas the graph of velocity and acceleration will come out to be a straight line with a negative slope, and finally the graph between displacement and acceleration will again be an ellipse. So this is the understanding of simple harmonic motion by the method of the reference circle. Now we have already seen that in simple harmonic motion we require a force which brings the body back towards its mean position. Such a force is also known as a restoring force. The nature of this force is given by the force law. The force law says that the restoring force acting on the body must be directly proportional to the displacement of the body at any given instant of time, which means that the force is always proportional to the displacement from the mean position. If we try to understand this with the help of the block and the spring, then we'll see that when the block begins to perform simple harmonic motion, then at the extreme position where the displacement is maximum, the force pulling the block back to the main position is also maximum. Similarly then, when the block begins to move towards the main position, because its displacement is decreasing, the force acting on the block is also decreasing in magnitude. And finally, at the main position, this force will go to 0 because the displacement has gone to 0. The same logic applies if the block was at the other end of the main position. In such a case again, at the other end, the force pulling it back towards the mean position would be maximum because the displacement is maximum. And then, as the block moves towards the main position, the force would go on reducing till it becomes 0 at the mean position. So I can say that F and X are directly proportional, and I will write down a constant of proportionality between them, that is K. Note that the negative sign indicates that the body is always bringing you back towards the mean position. So the force law simply says that F is equal to minus Kx. And this is one very other important way of defining what is simple harmonic motion. We already saw in the method of the reference circle that in simple harmonic motion, acceleration is proportional to displacement. And now we are seeing that the force is also proportional to the displacement. Both these statements are equivalent and both define what is the simple harmonic motion. Now this constant K is nothing but m omega square, and therefore F can also be written as equal to minus m omega square x. And we also know that omega is 2 pi by t, and therefore F is equal to 4 pi square m by t square into x. These are the different equations for the force in simple harmonic motion. Now let's ask the question, what is the frequency? Frequency is nothing but the reciprocal of the time period, so it's 1 by t given by omega by 2 pi, which is 1 upon 2 pi root k by m, which is equal to 1 upon 2 pi root a by x, where a is the acceleration and x is the displacement of the particle at any instant of time. Once you've answered the question, what is the force in simple harmonic motion, the next question is, what is the energy of a particle performing simple harmonic motion? And the two energies that we are concerned with are the potential and the kinetic energies. We already know the fundamental understanding of both these concepts. Let's try to see if we can write down what are the values of these energies. Let's say that the particle starts from the extreme position. At the extreme position, the velocity of this particle is going to be 0. In fact, that's why it starts moving back to the position, right? Its velocity is now 0. And if its velocity is 0, we know that the kinetic energy will be 0, and therefore I mark this pink dot at the origin. This pink curve will represent kinetic energy of the particle in simple harmonic motion. The green curve will represent potential energy. And at this extreme position, because the displacement is maximum, the potential energy will have some maximum value, which is given by the total value of the energy E. Why am I saying that at this point the total energy is nothing but the potential energy? This is because the total energy is kinetic plus potential. But there is no kinetic, and therefore the potential is the total energy, which I have denoted as E. So I mark this green dot at E. Now I move this block towards the mean position. When this block moves towards the mean position performing simple harmonic motion, I know that at the mean position the velocity of this block is the maximum. If the block is moving from right to left, then the velocity may be negative, but the magnitude is maximum. And kinetic energy depends on the square of the velocity, and therefore the magnitude of the kinetic energy will be maximum. However, at the mean position, there is no displacement of potential energy, and therefore potential energy is 0, and therefore at the mean position, all the energy is the kinetic energy, and therefore at the mean position, the kinetic energy is the total energy E, whereas potential energy is 0. Now as the block moves towards the other extreme, again kinetic energy goes to 0, while potential energy becomes the total energy. So you see that at any given instant of time, it is the potential energy which is either getting converted into kinetic energy, or the kinetic energy is getting converted into potential energy. However, it is important to note that totally their energy is remaining a constant. If now you also notice how much is the time period before the kinetic or the potential energy curves are repeating, then you'll see that the time period of the kinetic or the potential energy curve is t by 2, because they repeat after half of the motion, and therefore time period of ke or pe is said to be t by 2. We also said that the total energy is remaining constant. Either the potential energy is getting converted into kinetic or vice versa, but together they have one fixed number, and this fixed number is the total energy, which is given by the straight line marked at E. This is the total energy, the total mechanical energy, and it is constant for the particle throughout simple harmonic motion. And therefore the total energy is said to be independent of time. Finally, I want to just write down the formulae for all the three energies. The potential energy is given by half kx square. This is equal to half m omega square x square, which can also be written as half m omega square a square cos square omega t. The kinetic energy, on the other hand, will be half k a square minus x square, or we can write it as half m omega square a square sine square omega t. Finally, the total energy, which is the sum of the potential and kinetic energies, will be half Ka square, which is equal to half m omega square a square, which we just said will be a constant for a particle in simple harmonic motion. At the beginning of the chapter, we used the example of simple pendulum to talk about oscillatory motion in general. But now I want to come back to the simple pendulum and show you how this is actually an example of simple harmonic motion, provided of course the amplitude of oscillations is small. But for this, first I have to carefully define what is a simple pendulum. A simple pendulum is nothing but a heavy point mass attached to a light inextensible string suspended from a rigid support. The point where we suspend it from is known as the point of suspension, and the center of gravity of the heavy point mass is the center of gravity of the bob. And the length between the point of suspension and the center of gravity of the bob is known as simply the length of the simple pendulum. Now, in order to execute simple harmonic motion or oscillations in general, you will simply take this bob aside and then release it. And then when slightly pulled aside by a small angle theta and released, this bob will execute simple harmonic motion. This bob is oscillating between two fixed points which represent the maximum amplitudes of this bob on either side. Now let me draw the free body diagram of this bob at the extreme position. The forces that act on this bob at the extreme position are simply the weight of the bob acting downwards and the tension in the string acting towards the point of suspension. As you can see, we have resolved the weight into two components. One is the mg cos theta component acting opposite to the tension, while the other is the mg sin theta component acting tangentially to the circle that this simple pendulum is describing. Now let me ask you a question. You can see that there are three exact forces acting on the bob. There's T1, which is the tension, there's mg cos theta, and there's mg sin theta. Which of these three forces is causing the bob to come back to the mean position? It's very simple to see that it is the force of mg sin theta which is making the bob come back to the mean position. And therefore, by this simple analysis, I can say that mg sin theta is the tangential component of the weight of the bob which is acting towards the mean position and is hence, by definition, the restoring force. Just like that, in every situation or system in which simple harmonic motion is taking place, you will have to identify which is the restoring force by asking the question, what is making the bob or the object come back to the mean position? And therefore now I can say that the restoring force is mg sin theta. Of course, the negative sign tells me that it is always coming back to the mean position. Now, in order to prove that this motion is simple harmonic motion, I will have to prove either that the force is proportional to displacement or the acceleration is proportional to displacement. And to do that, I will have to take the torque about the point of suspension. And once I do that, I will write down the equation in terms of the angular acceleration and the displacement theta. So I want to tell you that this is actually an example of angular SHM. And on careful analysis, we find out that the expression for angular SHM is given by alpha is equal to minus mgl divided by I into theta. Here mg is nothing but the weight of the bob, L is the length of the simple pendulum, theta is the angular displacement, and I is the moment of inertia of this heavy bob. From here now it's easy to see that alpha comes out to be proportional to theta. But if alpha is proportional to theta, it means that this is angular SHM or angular simple harmonic motion. But if I'm dealing with simple harmonic motion, then I know that alpha should come out to be minus omega squared theta, because this is the form of the angular simple harmonic motion that we have learned even when we were dealing with the reference circle. There it was A is equal to minus omega square x. Here I'm saying alpha is equal to minus omega square theta, and on comparing the two equations, I get that omega must then be root mg by I into L. And from here comes the very famous equation for the time period of the pendulum. T is nothing but 2 pi by omega, and considering the fact that the moment of inertia of the heavy bob about the point of suspension would be ml square, I get the formula that the time period t is equal to 2 pi root L by g. Now I have found the time period of the simple pendulum, and I want to answer one final question. What are the factors that affect the time period of the simple pendulum? The time period of the simple pendulum only depends upon length and the acceleration due to gravity. If the length of the simple pendulum is fixed, then only those factors can affect the time period which will affect the value of g. And we learned in the chapter gravitation that the value of g is affected by height in the way that gh is equal to g 1 minus 2h by r, where r is the radius of the earth and h is the height of the object from the surface of the earth. But g is also affected by depth, and therefore gd is equal to g 1 minus d by r, and by this equation g will change, and this will again affect the time period of the simple pendulum. It will also be affected by weightlessness, that is, if small g is equal to 0, then because g is in the denominator, time period will reach infinity. And finally, there will also be an effect of the density of the medium in which the simple pendulum is oscillating, and this density of the medium will lead to a change in the effective acceleration due to gravity, and therefore g dash will be g 1 minus rho by sigma, where rho is the density of the liquid in which you have placed the simple pendulum and sigma is the density of the bob. So all these factors that affect the acceleration due to gravity will lead to an effect into the time period of the simple pendulum. The main thing to remember is that the simple pendulum is performing simple harmonic motion. Now I have shown that in case of the simple pendulum it is performing angular simple harmonic motion, but of course we can also approximate this and show that it is performing linear simple harmonic motion. So instead of saying that alpha is proportional to theta, you will also be able to show A is proportional to X with some approximations. Another system that is worth studying about when it comes to simple harmonic motion is the oscillations due to a spring. Now, the oscillations due to a spring is one of the simplest observable cases of simple harmonic motion. In this case, I have a spring, as you can see, and this is the original length of the spring. However, the end point of the spring, which is free, this is not the mean or the equilibrium position. The position that you have to consider is when you attach a mass to the spring. Once you attach this mass, you will see that it causes the spring to be stretched downwards. This is the mean or the equilibrium position of the object. Now if I pull this object downwards by a small distance and release it, then this spring will cause the object to perform simple harmonic motions between two fixed points, that is the points of maximum amplitudes minus A and plus A. Now, just like the simple pendulum, I want you to think and analyze, in this case, what could possibly be the restoring force for this system. This is the clue to understanding any simple harmonic motion problem. Understand which is the force causing restoration. In this case, it is simply the spring. And the spring is governed by Hooke's law, which we know is nothing but the force is equal to minus kx. And therefore, I say that the restoring force is equal to the spring force, that is equal to minus kx, where k is the spring constant. And therefore, k's value depends upon the elastic properties of the material of the spring. Now, from this, I get the time period of the spring pendulum, which is 2 pi root m by k, and omega is given by root k by m. Now, here, k is nothing but the force per unit displacement, and m is the mass that we attach to the spring. And therefore, if two springs are in series, we know that if two springs of spring constants k1 and k2 are in series, which means they are attached end to end, then their equivalent or the resultant spring constant will be given by 1 by k is equal to 1 by k1 plus 1 by k2. And if the two springs are in parallel, then the resultant is just the addition of both the spring constants. Therefore, finally, I want to tell you that the value of k depends on the material, and if you have a very large k, it means the spring is very stiff, and if you have a very small k, it means the spring is soft. Now, everything that we've been saying about simple harmonic motion is sort of ideal, which means that in actual practice, it's very hard to find situations where pure simple harmonic motion is taking place. Now, what do I mean by that? What I mean is if you allow a system to undergo oscillations, for example, if you allow a mass to undergo oscillations due to a spring, you will see that after some time, these oscillations will die out. And why exactly do they die out? They die out because of their contact with the surrounding medium. For example, in the case of the oscillations due to a spring, it could be the air drag, it could be the friction at the point of suspension. The point is that there are opposing forces which are opposing the motion or the oscillation of the heavy mass. These opposing forces cause the system to lose energy continuously. And because the system loses energy continuously, the system eventually stops performing oscillations. Such oscillations which die out in time are known as damped simple harmonic oscillations or simply damped oscillations. So what I want to point out is that because the system is continuously losing energy, the angular frequency for simple harmonic motion, which we have said so far, that is omega is equal to root k by m, this value may not always be true. Because in the presence of damping forces such as air or friction, we will see that omega will be much less than root k by m, because there is a loss of mechanical energy of the spring system in this case, which appears as heat to the system and the surroundings. So now if you observe the displacement of the oscillations of the spring with time, you'll see that the amplitude of these oscillations starts out correctly, but in time these amplitudes get smaller and smaller and eventually die out. So therefore, this shows us that there are always damping forces present in real and practical situations. Damping force offered by the medium is generally proportional to velocity of mass executing the simple harmonic motion and acts opposite to the direction of velocity. This is given by the formula that Fd, which is the damping force, is equal to minus Bv, where B is a positive constant that depends upon the characteristics of the medium and the size and shape of the block. Also, this equation is valid for small values of velocity. So this means that in addition to the restoring force acting on the system, there is also the damping force acting on the system. And from Newton's second law, then I can say that the total force is just minus kx, which was the restoring force, plus the damping force, which is minus bv. So the total force F is equal to minus kx minus bv. And as a result of this damping force, we saw that the amplitude of the oscillation goes on decreasing, and the equation that describes how the oscillations or how the amplitudes are decreasing with time is given as x is equal to xm e raised to minus bt by 2m, where t is the time at any given instant. So if in reality all oscillations will die out because of damping forces, then what can I do to keep the oscillations going? And that brings me to the idea of free and forced oscillations. So first let's understand that the oscillations of a body are of two types. One is the free oscillation and the other is a forced oscillation. Free oscillations are those that when a body is excited and released, then the oscillations that it performs are known as free oscillations. So what does this actually mean? It means that the oscillations are taking place only under the action of restoring force. There is nothing else that is bothering the object which is trying to perform oscillations. In such a case, the oscillations are said to have a fundamental or a natural frequency, because this is the frequency decided by the object alone and not by anything external. This natural frequency has a formula given by 1 upon 2 pi root k by m. However, we saw that because of the presence of damping forces like the viscous drag due to air, the pendulum in this case will oscillate with decreasing amplitude and finally come to a rest, which means that the damping forces will cause it to eventually die out in amplitude. So this means that free oscillations generally just keep on dying out. So like I asked the question before, what do I do so that the oscillations don't die out? What I do is I keep providing it with external energy, because the system is continuously losing energy because of the damping force. I simply have to give the energy back, and to do that I will give it an external force. So this brings us to forced oscillations. To overcome the damping forces, an external force is required, and therefore these oscillations which occur under an external force are known as forced oscillations. In forced oscillations, the frequency of the damped oscillator, that is the frequency of the object, is equal to the frequency of the external periodic force. For example, in the case of this simple pendulum, when I take it to one side and release, I know that after some time the oscillations might die out, so I make sure that I keep pushing this pendulum again and again. But as you can see from the graph, the frequency of the force that I'm applying is much higher than the frequency which it naturally had. The natural frequency is represented by the curve, that is the dashed white line. However, the frequency that I am supplying as an external force is the yellow line. And what the pendulum is actually performing is the frequency under the yellow line. Therefore, I can say that the oscillator or the object always takes the frequency of the external force. However, when the frequency of the driving or the external force is close to the natural frequency of the oscillator, this leads to a large increase in the amplitude of oscillations, and this is a phenomenon known as resonance. So this wraps up all the concepts that I want to revise with you under the umbrella of oscillations. I hope you enjoyed this video. Thank you for watching.